What if the universe we inhabit isn't what we think it is? Recent results from the James Webb Space Telescope are pressing on our assumptions. A fresh analysis of galaxy rotations hints at a surprising pattern. More galaxies appear to spin the same way than randomness should allow. That challenges the long-standing idea that the cosmos is isotropic, uniform and directionless at the larger scales. It even raises a radical possibility. Our entire universe might be the interior of a black hole. Join our journey to decode the cosmos. Hit subscribe and tap the bell so you don't miss the next leap. Webb was built to look far back in time, catching ancient light stretched by expansion. By studying galaxies that formed a few 100 million years after the Big Bang, James Webb offers a direct glimpse of the universe in its earliest chapters. In one study, led by astrophysicist Lior Shamir, researchers examined 263 young galaxies and tagged their apparent spin directions. Roughly 60% of those galaxies seem to rotate clockwise, while about 40% look counterclockwise. It's not a huge skew, but it's meaningful if confirmed. In a perfectly isotropic cosmos, clockwise and counterclockwise should balance out on big scales, much like fair coin flips average to even odds. Earlier Hubble hints pointed the same way, but Webb's sharper vision makes the bias harder to dismiss as noise, selection effects, or small sample luck. Spin imbalance implies a global memory, a cosmic handedness written into initial conditions. Standard cosmology predicts no preferred direction. Gravity should sculpt structure without favor. If the early universe truly leaned one way, something set that preference. Was there a cosmic axis? A rotational imprint baked into space-time before galaxies ever formed? One bold framework suggests our universe could be the inside of a black hole that formed in a larger parent cosmos. In this picture, the Big Bang wasn't a creation from nothing but the rebound of a collapse. Matter falls inward, conditions become extreme, quantum rules stiffen the fabric, and instead of a singularity, the collapse halts and bounces, launching a new expanding region, ours. Quantum mechanics forbids identical fermions from sharing the same state. This is the Pauli exclusion principle. Squeeze fermions hard enough, and degeneracy pressure pushes back. That pressure props up white dwarfs, and neutron degeneracy props up neutron stars. In extensions of relativity such as Einstein-Cartan theory, the intrinsic spin of particles twists space-time, torsion, which can act repulsively at ultra-high densities. Put these ingredients together, and a credible sequence emerges. As collapse drives densities upward, quantum pressure and spin-induced torsion stiffen space-time. Infall slows, then stalls. For a brief moment, pressure wins over gravity, and the interior rebounds. That rebound ignites a super-hot, rapidly expanding phase that, to observers inside, looks exactly like a Big Bang. Tiny quantum jitters stretched by the bounce become small ripples in density, seeding the galaxies we see today. No singularity required, just known principles pushed to their limits. If you love deep, testable ideas about space, tap subscribe to Quantum Leap. It helps more curious minds find these explorations, and it keeps videos like this coming. If the parent black hole was rotating, its angular momentum could seed a preferred direction inside the newborn universe. That inherited spin might show up statistically in galaxy rotations, in alignments across vast scales, or as subtle patterns in the cosmic microwave background. A mild excess of one winding over the other could be the faint echo of that origin story. A black hole bounce origin may also connect to other tensions. Consider the Hubble tension, the disagreement over the universe's expansion rate measured by different methods. If early time physics deviates slightly from the vanilla Big Bang picture, a bounce framework might soften that rift. Likewise, JWST has found surprisingly massive, mature galaxies earlier than expected. If our cosmos inherited seeds, primordial black holes, or overdense patches from a pre-bounce phase, early growth could accelerate, making those impossible galaxies less mysterious. Extraordinary claims demand extraordinary evidence. The spin result needs larger, cleaner samples across many sky patches. We must control for biases, image orientation, point spread asymmetries, weak lensing distortions, and how spiral winding is inferred at extreme distances. Our vantage point within the Milky Way could nudge statistics if we're not careful. That's how good science works. Tighten the methods, then see which ideas survive. Multiple independent lines of evidence. First, a robust, reproducible spin asymmetry across instruments and surveys. Not just one field, not just one pipeline. Second, signatures of an early preferred axis in large-scale structure or background radiation, consistent with a shared direction. Third, relics that fit a pre-bounce epoch, specific distributions of primordial black holes, or a gravitational wave background with a telltale spectrum. None of these alone would seal the case, but together they'd point strongly. If the Big Bang was a bounce inside a rotating black hole, then black holes are not dead ends, they're cosmic wombs. Each black hole could spawn a baby universe with its own parameters, some hospitable to complexity, others not. Over countless generations, universes that make more black holes proliferate. That cosmic natural selection could nudge physical constants toward values that favor structure, chemistry, and long cosmic lifetimes. None of this erases what works. Lambda CDM. The standard model with dark matter and dark energy beautifully explains the cosmic microwave background, element abundances, and the web of galaxies. Any bounce model must reproduce those successes while extending the story. Think of it not as tearing down the house, but adding a deeper foundation beneath it. A mechanism for the initial conditions we usually take for granted. Deeper web fields will expand spin catalogs dramatically. Radio arrays and integral field spectrographs can measure true kinematics, not just apparent winding, reducing classification bias. Wide surveys will map alignments over gigaparsecs, challenging or corroborating a preferred direction. Gravitational wave observatories and pulsar timing arrays can hunt for subtle backgrounds predicted by bounce scenarios. On the theory side, models must make crisp, falsifiable forecasts, not post hoc stories that explain anything and predict nothing. Humans evolved on one small world, yet we can now test ideas about the birth of space-time itself. That's astonishing. Whether the spin bias fades or firms up, the process of checking it will sharpen our tools and deepen our understanding. If the imprint holds, we'll have glimpsed a thread that ties our sky to a larger cosmic tapestry. If it fades, we'll still have learned how to read the universe more carefully. Do you think a preferred spin is real, or is it a mirage that better data will wash away? Could a rotating parent black hole have stamped our universe with a direction? Tell me your take below, and if you want more investigations like this, subscribe to Quantum Leap and share this video with a friend who loves big physics. Maybe the universe isn't a perfectly even coin toss. Maybe it remembers how it began, and that memory is written in the gentle twist of distant galaxies. If so, the night sky isn't just a picture of our past. It's a signature from before our beginning, inviting us to read it, carefully, skeptically, and with wonder.